So what we'll look at now is the concept of gas effusion and diffusion. They sound the same, but they're a little different. Effusion is the passing of a gas through a small hole into a vacuum, an evacuated chamber. So if you have two chambers here, and there's gas on one side, and there's a vacuum, meaning the absence of all matter, on the other side, and you have a pinhole in the separator between them, then the gas particles, which are bouncing around like crazy, are eventually going to hit that pinhole. And having nothing to push back against them, nothing to collide and knock them out of there, they're going to travel into that hole. That's what effusion is. Diffusion, however, is when gases mix. So in diffusion, you have a situation where gas particles are not only going to be moving, but they're going to be hitting other particles of other gases, like the air. For example, if we allow certain substances to diffuse, they have to work their way through the air. There's air molecules getting in the way. Okay. Now, effusion is governed by Graham's law, and Graham's law is fairly simple. It's a ratio. So we look at the rate of effusion for gas 1 compared to the rate of effusion for gas 2, and that's going to be equal to the square root of the molar mass of gas 2 over the square root of the molar mass of gas 1. Pretty straightforward. Okay. So all of this is going to depend on the average velocity of the particles. The faster particles are moving, the more likely they are to go through that little pinhole. Right? If they're not moving as fast, they're not going to hit that area often enough to get through. So, for example, compare the effusion rates of hydrogen and oxygen gas. So, the way we'd set this up is the rate of hydrogen gas effusion to the rate of oxygen gas effusion, square root of the molar mass of oxygen to the molar mass of H2. That's the square root of the molar mass of oxygen, which is 32, over the square root of the molar mass of hydrogen, which is 2. Square root of 32 over the square root of 2 is equal to 4. So that means that hydrogen effuses 4 times faster than oxygen does. Okay? Does that make sense? Well, yeah, the particles of hydrogen should be moving more quickly because they're smaller. So the same amount of kinetic energy is going to be applied to both. Hydrogen gas particles are going to move faster because they're lighter. Okay? So the difference between these two here is if you have, for example, gases mixing, they're going to have to collide with each other, and it's going to take longer. Whereas if you have gas just traveling through a pinhole into a vacuum, it should go fairly quick. The last section here that we want to take a look at is what do we mean by real gases versus ideal gases. And we looked at this previously in another video, but just to remind ourselves. So an ideal gas is a gas at all temperatures and pressures. Okay? Particle size is fairly small compared to the space between particles. There's no interaction between particles that we would consider. And at high temperature and low pressure, real gases will behave this way, but an ideal gas behaves under these conditions all the time. Okay? For real gases, you have to take into account intermolecular interactions, like are the gas particles attracted to each other? Is there hydrogen bonding that might happen? Are they polar molecules that might be attracted to one another? Because if they are, that's going to affect things like their volume. It's going to affect their velocity if they're attracted to each other. The size of the particle is now important compared to the space between them. So if you decrease the volume of a real gas and you have got large particles, it's not going to take very much before those particles come in contact with one another, and therefore you have a liquid. Okay? So under conditions like low temperature or high pressure, real gases are no longer gases. And if they're not gases, then the gas laws don't apply. So you have to think about that. Most of the calculations you'll do in this area are going to be on ideal gases because we don't want to take into account all of these. All of these factors now with real gases bring in a lot more complexity to the calculations. So we'll generally do them with real gases, with ideal gases, even though we may be calling them real gases.